Okay, so the suggestion was to look for a K5 inside of this graph, and although there are a lot of vertices of degree 4, there are not 5 vertices of degree 4 that are all connected to each other. So I'm not going to be able to find K5 in that graph. But could I maybe find a K33? That's our last hope, so I hope that there is one. Do you see one? So K33 basically means I need 6 vertices. I need 2 camps of 3 each. And in one of my camps, the vertices will be not connected to each other, but they will connect to all 3 of the vertices in the other camp.
Got it.
Do you know how to do it?
Mm-hmm.
Did you find 2 camps?
I found K33.
Oh, wonderful. Tell me what your vertices are.
On
make 2 sets out of it.
So the first set is EIC and the second set.
Stop.
Okay.
EIC. I don't want you to tell me the second one. I want everybody to look at this.
Okay.
EIC. Guys, look at this right here. EIC. Are any of those 3 vertices connected to each other? No, so they can be in one of my camps. Now, Joseph already knows the answer, but he's not going to tell. What I want you guys to think about is what would be the other camp that I would put the squares around, right? We do circles and squares. H, and D, and J. Does that work? Wow, that works. H, D, and J are connected to H, D, J. There we go. H, D, and J are connected to E, I, and C. And see, all of the other 9 vertices that are on that graph are actually just there throwing us off. They're not part of the K33. But if, for example, this part of the graph over here, I don't need it anymore, right? I can start erasing everything that's not involved in those 6 vertices. And even edges like the edge from G to H, you get rid of it, because G isn't really part of my 2 camps. By the time you erase every edge and every vertex is not part of this 2 camps that I've given you, you will have exactly an isomorphic representation of K33. This one's tricky because you don't clearly see the K33 staring at you. You actually have to find it in the graph with all these other extra edges kind of in the way, confusing you. Does that make sense? Okay. Don't forget that trick. If the edge count doesn't work out, 27 and 39, and you don't have any other tools, look for K33 and look for K5. Chances are, if it's a really tough one, like I thought this was pretty tough, I probably would give you the answer. I wouldn't say yes or no, I would give you the answer. I don't want you spending, an hour trying to redraw this as a planar graph when it's not even possible. Okay, did I reproduce the original figure correctly?
Except for the extra edge.
Oh, this shouldn't have been here. Right. Okay, I'm just going to leave it there for now. I have one last question. This one's an easy one, I think. It's fairly quick. Find a spanning tree for this graph. Last thing. How do you find a spanning tree? We haven't talked much about trees today. Let me just tell you, you should review the proofs that we did. We had a fairly proofy lecture, I think it was a week ago on Wednesday, in section 11.5, where I proved a lot of things about trees. They have no cycles. They have exactly n-1 edges. They have unique paths between any 2 points, any 2 vertices, right? All of those theorems, I could ask you to prove any one of those. It's in the review packet that I said specifically, please do review those proofs. Because they're not that bad. But it'd just be good to get it back in your head again. Let's see. Lisa, do you want to... You're not going to give me a whole span. I just want to know, what's your strategy for coming up with a Spanish?
Oh, well, we know that, I kind of just ignored all of the curvy lines, so I just looked at the 8 boxes You
Okay,
know what I mean?
yeah,
And then,
but I mean, what are you trying, I mean, I wanna know,
well,
what's
we're
the
just
strategy
we're basically just trying to create a tree that involves all 15 vertices.
that uses those edges, right?
Yeah, so
Okay.
I
So-
kind of thought of what a rake looks like.
Okay,
So,
that's not what I want is, I'm still not getting quite, maybe somebody else knows what I'm trying to ask here. What is the strategy that will create a spanning tree for you? Laura? Exactly, remove all non-bridges is really the point. So if I see any cycles in the graph, I need to remove those edges, that's what I was getting at.
okay.
And you were doing that, it's just, I wanted to get that spit out, because that's the key thing. So you just remove all edges that are participating in a cycle. Okay, so let's just do this as a team. Let's see. Adriana, can you tell me an edge that I can remove? So, BG, I think you can take off almost any edge right now. See, the point is, anything that's part of a cycle, we can take off. So BG, you can't go wrong, all right? Rocky, give me another edge to remove. KL, all right? We're just gonna keep taking off edges. Peter, what's another one?
No.
Hmm?
And
Oh!
Got you back,
I
got
thought
you
you
back.
were saying I can't do it, I'm like, I'm
Did that
stuck
just out of
already.
there.
Anybody else? Anthony, give me another one. BD, all right, that's part of a triangle. Annalise, how about you? Do you want to take off an edge?
HE.
HE, all right, get rid of that one. Sounds good. Let's see, Jason, do you want to take off another one? CJ, so we're getting rid of these diagonals, so it's easier to see it. I still have this edge here though. Okay. Let's see, Joseph, do you want to give me another one?
FM.
FM. All right, got rid of that. Let's see, Jeff, how about another one? FA is part of this cycle, right? Okay. Getting a little harder now. Alex, do you have another one we can remove? EJ over here, all right. Certainly works. Okay, Nicole? GL, that's part of this square right here, so we'll take that out, all right. Mark, do you have another one?
DI.
Okay, DI. I'm just gonna keep asking you for them, and at some point, we're not gonna be able to do it anymore, so just be ready for it. I'm just gonna keep asking until we get to where we can't do it any longer. Lisa, do you wanna take off another one?
And
NI is part of this little square here, all right, good.
we're done.
No.
Peter, do you wanna take off another one?
Natural log.
Oh, and natural log.
My gosh.
Oh, I didn't see that one. Now we're done.
How are we gonna check that we're done, because in case we screwed it up? You could check every edge, just make sure removing it disconnects the graph, but there's a better thing we can do. Yeah, count how many edges are left. How many edges should we have at this point?
And then
N minus 1, which is, in this example, 14, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We're done. We did it. Okay.
Yay.
Guys,
More side of duty.
I didn't give you any practice on crossing numbers today, but we just did it in the homework, so I don't think I need to go over that again now. I think we should call it a day.